Hello, this is Professor Pearson, and welcome to Chapter 10, Hypothesis Testing. In Chapter 10, we will only cover two sections, Section 10.2 and Section 10.3. Of course, you can read the whole chapter if you decide to, but we're only covering for this class Sections 10.1 and 10.2. Let's begin our chapter on hypothesis testing by first establishing some definitions. The definition for a hypothesis is a theory or premise, usually the claim that someone is investigating. Next, the null hypothesis, which is H sub O, describes the currently accepted value for the population parameter. Next, we have the alternative hypothesis, H sub A, and that describes the claim that is being tested, the mathematical opposite of the null hypothesis. And then lastly, hypothesis test. And a hypothesis test compares the merit of the two competing hypotheses, the null hypothesis and the alternative hypothesis. And it does that by examining the data that is collected. So what is a hypothesis test? Let's take a look at it. In a hypothesis test, the null hypothesis is always given the benefit of the doubt. That means that we agree with it, we believe it. That is, we assume that the null hypothesis is true unless there is an overwhelming evidence from the sample that goes against the null hypothesis. First, let's take a look at how to write the null and alternative hypothesis. First, we want to write down the claim, and that is the null hypothesis. Then we want to write down the mathematical opposite of the null hypothesis, and that would be the alternative hypothesis. Next, we want to assign the null hypothesis and the alternative hypothesis labels. Remember that the null hypothesis is the currently accepted value for the population parameter. The label or symbol for the null hypothesis is H sub O, or H sub 0. The alternative hypothesis label or symbol is H sub A, or hypothesis alternative. Next, let's take a look at an example. Let's see how we can determine the null and alternative hypothesis. Here's the scenario. It is generally accepted among leading educators that the average student studies no more than 15 hours per week. In the spring newsletter, a national student organization claims that its members study more per week than the average student. Solution: let's look at the claim. The claim is that members of the National Student Organization study more per week than the average student. Remember, we've stated that the average student studies no more than 15 hours per week. So our mean, or the average, of the population, mu, is greater than 15. And the mathematical opposite is that the mu, or mean, is less than or equal to 15 hours per week. So that says to us that the H sub 0, or H sub O, which is the null hypothesis, is that the mean is less than or equal to 15 hours per week. That's the accepted belief. That's what the leading educators said on average, that students study no more than 15 hours per week. Next, we have our alternative hypothesis, which is the mathematical opposite. And that states that the mean or average number of hours studied per week by students is greater than 15 hours per week. and that is the amount that the National Student Organization claims. So we're testing the hypothesis. Let's take a look at another example of how we state the claims of our hypothesis. This way we'll get a feel for how to collect the scenario information and then write a hypothesis from it. So we'll determine the null and the alternative hypothesis. A leading news authority claims that the president's job approval rating has dropped over the past 3 months. Previous polls put the president's approval rating at a minimum rate of 56%. The president's chief of staff is concerned about this claim since it is an election year, and he wants to run a test on the claim. First, let's take a look at the claim for our solution. The president's approval rating has dropped lower than 56%. So we use symbols to say the probability is less than 0.56 or 56%. Next, let's take a look at the mathematical opposite, which we know is the alternative hypothesis. And that's stated as the probability is greater than or equal to 0.56 or 56%. Let's put it into symbols. Our null hypothesis H sub O or H sub 0 is P greater than or equal to 56%. That's our current accepted belief, our null hypothesis. And our alternative hypothesis says that the p-value or probability is less than 56%, testing hypothesis. So those two hypotheses will be tested one against the other. Next, let's look at some additional definitions to help us increase our understanding of hypothesis testing. First, we have the test statistics, and that's a component of the criteria used to evaluate the hypothesis, which is calculated from the sample data gathered. Then we have what's statistically significant, and that's when data is said to be statistically significant. It is unlikely that a sample similar to the one chosen would occur by chance if the null hypothesis is true. So we're taking a look at statistically significance based on the likelihood that a sample similar to the one chosen would occur by chance if the null hypothesis is true. And lastly, the level of significance, or the alpha, and that describes the claim that is being tested, the mathematical opposite of the null hypothesis. It is always the complement to the level of confidence, which is the symbol C, where alpha equals 1 minus C. So our level of significance equals 1 minus the level of confidence. Next, let's go to the steps for hypothesis testing. First, we want to state the null and the alternative hypothesis. We've learned how to do that in previous slides. Then we want to set up the hypothesis test by choosing the test statistic and determining the values of the test statistic that would lead to rejecting the null hypothesis. Then we want to gather the data and calculate the necessary sample statistics. And lastly, we want to draw a conclusion. Now let's take a look at the only conclusions for a hypothesis test, or for hypothesis testing. The only conclusions we can draw is we can reject the null hypothesis, or we can fail to reject the null hypothesis. Once you have decided on a conclusion, a discussion of the meaning of this conclusion in terms of the original claim is appropriate. And what that means is once you determine whether you will reject the null hypothesis or fail to reject the null hypothesis, you have to state why. Let's take a look at an example. We're going to determine the null and the alternative hypothesis using this scenario. It is generally accepted among leading educators that the average student studies no more than 15 hours per week. In their spring newsletter, a national student organization claims that its members study more per week than the national average. After performing a hypothesis test at the 95% level of confidence to evaluate the claim of the organization, the researcher's conclusion is to reject the null hypothesis. Does this support the organization's claim? Well, let's take a look. Here's our solution. First, the claim. The claim is that the members of the National Student Organization study more per week than the average student. And that is represented by mu is greater than 15, or average is greater than 15 hours of study per week, says the National Student Organization. Our mathematical opposite, or our competing claim, is that the average number of hours of student studies per week, says the leading educators, is less than or equal to 15 hours of study per week. So for our null hypothesis, we have the average less than or equal to 15. That's the current accepted belief by the leading educators. And then our competing, or our alternative hypothesis, says that the average number of hours studied per week, claiming the National Student Organization, is greater than 15 hours per week. Since the null hypothesis was rejected, the organization can be 95% confident in its claim that its members study more per week than the national average. So this is a good way of taking a scenario and saying exactly what does it mean. We do our work, we set up our symbols, we carry out our calculations, and then we interpret our decision. Now, how does this work for test statistics for samples where our sample size n is less than 30? And remember, we said 30 was the central limit theorem. That is our number of samples that is sufficient, the number 30. So what do we do when we have test statistics for samples that are less than 30? We use our t-score value, our sample average minus our population average, divided by the standard deviation of the sample divided by the square root of the number of samples. And remember that our degrees of freedom, or df, equals n minus 1. To determine if the test statistic calculated from the sample is statistically significant, we will need to look at the critical value. The critical values for n less than 30 are found from the t-distribution table. Now let's take a look at how we find the critical value. Let's take a scenario. We're going to find the critical t-score for a right tail test that has 14 degrees of freedom at the 0.025 level of significance. So for our solution, our degrees of freedom equals 14, and our level of significance, or alpha, equals 0.025. So we take our t distribution table at our level of significance of 0.025, and the table indicates that that equals 2.145. So as we look at if we're going to accept or reject, let's take a look at rejection regions. To do that, we need to determine two things. The rejection region is determined by two things. Number one, the type of hypothesis test. Number two, the level of significance, or alpha. Finding the rejection region, we want to look up the critical value, our T sub C, or our critical value on our T distribution table, and we do that to determine the cutoff for the rejection region. Next, if the test statistics you calculate from the sample data falls in the level of significance, or alpha area, then reject the null hypothesis. So after establishing some foundations, let's take a look at the types of hypothesis test. We have the alternative hypothesis type of test, and that's where we have the value is greater than. And the type of test we would utilize would be the left-tailed test. Then we have the alternative hypothesis, where the value is less than, and that would have us use the right-tailed test. Then we have where in our alternative hypothesis the value is not equal, and that would give us the use of the two-tailed test. Now let's take a look at what that would look like in terms of rejection regions for left-tailed test and our alternative hypothesis, where it contains a less than a value. So we've got our rejection area and our fail to reject the null hypothesis area. So we reject if our T value is less than or equal to the negative T sub value for the level of significance. So we've got our alpha value there, or our level of significance, and we see our cutoff point and our rejection area. And then on the other side we have the fail to reject the null hypothesis. So we know if we fail to reject the null hypothesis, then that means that we agree with it. If we reject the null hypothesis, then that means that we don't agree with the null hypothesis, but we have taken on the alternative hypothesis. Now let's take a look at a visual where the rejection regions for the right-tailed test for our alternative hypotheses contains a greater than. So in our visual representation, we reject if our T value is greater than or equal to our T level of significance. So in this visual, we've got failed to reject the null hypothesis. We've got our cutoff point at our T sub-level of significance, or our alpha region, where we reject the null hypothesis. Next, let's take a look at our rejection regions for two-tailed test of our alternative hypothesis, which contains a not equal to. We can see right in the center we have a fail to reject the null hypothesis. So if we fail to reject the null hypothesis, then we agree that the null hypothesis is accurate, that it's true. But we can see on the outer two tails we reject the null hypothesis. And so we've taken our level of significance, divided by 2, so that we can get the two tails, one on the lower end and one on the higher end. And we've got our cutoff points there. So now, once again, let's take a look at the steps for hypothesis testing. Number 1, state the null and alternative hypothesis. Number 2, set up the hypothesis test by choosing the test statistic and determining the values of the test statistic that would lead to rejecting the null hypothesis. Number 3, gather data and calculate the necessary sample statistics. And lastly, draw a conclusion. What have you decided? What have you concluded? What has been your interpretation? Okay, let's take a look at an example by using a scenario. We have 27 college students, and they are asked how many parking tickets they get a semester to test the claim that the average student gets more than 9 tickets a semester. The sample mean for the number of tickets was found to be 9.8. with the standard deviation of 1.5. Use an alpha or level of significance equal to 0.10 or 10%. For our solution, we know that n equals 27. That's the number of college students. We know that our population average is 9 tickets a semester. We know that our sample average is 9.8 tickets per semester. Our standard deviation is 1.5, and our degrees of freedom equals 26, which is n minus 1, 27 minus 1, so our degree of freedom is 26. And then our level of significance, or our alpha, equals 0.10 or 10%. First, let's start with our t for our level of significance. And on our chart, that equals 1.315. And taking our t-score formula, we've got our sample average minus our population average divided by our standard deviation divided by the square root of our sample size. And so as we plug in our numbers, we have 9.8 minus 9 divided by 1.5 divided by the square root of 27, and that equals approximately 2.771. Since the t-score is greater than our level of significance, our t alpha or t level of significance, we will reject the null hypothesis. So in conclusion, let's take a look at some definitions about the possibility that we might make an error in terms of rejecting the null hypothesis or failing to reject it. So the type of errors we can make are a type 1 error, which is represented with the symbol alpha, and that's the probability of rejecting a true null hypothesis. The other type error we might make is a type 2 error, and that's represented by the symbol beta, and that's the probability of failing to reject a false null hypothesis. And here we have a chart that will guide us into the definitions of possible errors. So if we make a decision, and that decision is to reject the null hypothesis, when in reality the null hypothesis is actually true, we've made a type 1 error. If we make a decision to reject the null hypothesis when in reality, when actually the null hypothesis is false, we've made a correct decision. Now if we make a decision to not reject the null hypothesis when in reality the null hypothesis is true, we've made a correct decision. But if we decide to not reject the null hypothesis and in reality the null hypothesis is false, we've made a type 1 error. So as we create our hypothesis, give them symbols, find our test statistic, measure that against our level of significance, our level of confidence, and then we come up with a decision. If we've indeed made an error, we can see that it will either be a type 1 error or a type 2 error. That concludes our look at hypothesis testing. I hope you enjoy Chapter 10, Sections 10.1 and 10.2. And remember, hypothesis testing requires us to have a somewhat convoluted view of whether we will accept or reject the null hypothesis. And what I mean by that is you're going to have to study this and reflect on it, meditate it, think about it a while in order to get the thinking required for hypothesis testing.